project supervised by Evelina Peltola, and I will present some of the results. I will start with the Weyl anomaly, which I hope is something you might be familiar with. When you have the partition function of a conformal field theory, this is dependent on the metric, and then if you change the metric by a conformal factor, so a local rescaling, then it varies by the central charge and the two metrics involved. And this factor is, you can call a Liouville action, and it's defined as follows. So you have the, let's define it for two arbitrary metrics, G1, G2, which will be related by sigma. So there is there's the divergence squared of the conformal factor, and then there is some term related to the curvature, and it's an integral over the surface. And there is a nicer way of writing this for surfaces without boundary or with some specific restriction on the boundary, which is a more symmetrical way, and which also is why I wrote this as some kind of pairing between the metrics, which looks as follows. These factors phi, they are the local rescaling of the metrics with respect to a flat metric, because they need to be in the same conformal class, and we pick a conformal class such that locally we can write the metrics as dz bar, and then we have that gi is dz bar rescaled by this phi locally, so you might need to sum over like a partition of unity. And this pairing now has some nicer properties, which allows us to absorb this conformal factor into a one-dimensional vector space associated with the surface, which will become this modular functor. So the surfaces I'm concerned with are surfaces with boundary. This is because they are part of the domain for the functor in a Siegel-type conformal field here, but maybe a nicer way of seeing why we need boundaries is because I'm working in genus 0. So if you have a higher genus surface, then you can always decompose it into genus 0 parts, but then the parts, they have boundaries. And to be able to put them back together, you need to have parametrized boundaries. So my boundaries will have some parametrization zeta coming from the circle, and they are analytic because we are working with Riemann surfaces. So that means that around the circle there is some annulus, such that it becomes a holomorphic map on this annulus. And then for this to still hold, because there's some boundary between these, we need a specific type of metrics. So we only need to take those metrics, which, if you pull back from this parametrization, become a flat metric on around the circle. In Siegel CFD you have incoming and outgoing boundaries, and you only sew the incoming ones to the outgoing ones. So there's actually two different types of restrictions. So for the zeroth one, the zeroth boundary, we have to do an inversion such that this flat metric matches with what is going to be. So this J is Z to 1 over Z.
What is a zeroth boundary?
So our surfaces always look like this. And then the zeroth boundary is like the incoming one. And then there are some other boundaries. There are the outgoing ones. And then the sewing only happens in a way that we sew some incoming ones to outgoing ones. And then you want the metrics to match here. So if you have this thing, then there is an inversion in the gluing, and this makes it in such a way that they match together. So one example of such a metric on an annulus is that it looks like some kind of vase. Let's try drawing it like this, such that here it looks like the outside of the unit circle, and here it looks like part of the inside of the unit circle. And you can see if you like copy this thing below it, then this part fits exactly into this one. There's other choices you can take. You can also, for example, take the round metric, then these would actually, could be the same. Okay, and this implies, if you take these kind of metrics, that this sigma is always 0 near the boundary. Okay, and now we get some properties of this Liouville action, which one of which is the cocycle property. And that's if we take 3 metrics, then the middle one cancels. And there is also anti-symmetry, which you can see from the minus here. And there is diffeomorphism invariance, which means that if we take the pullback metric along some diffeomorphism preserving the boundary parametrizations, then this preserves the pairing. And I will use this to define the determinant line which is, for example, the partition function should take values in if you don't want to choose a metric. So this determinant line, it's will be denoted a real determinant line. There's also a complex one. And what we do is we take these special metrics. It's the conformal class, but then with some extra property, which is this thing on the boundary. And there's then we take some multiple of it, and then there is a equivalence relation where there's lambda 1 and B1, and lambda 2 G2. Then we want that lambda 1 is exactly varied by this factor with respect to the G2, lambda 2. And by this, we can have a one-dimensional vector space. This becomes a vector space with some addition which uses this cocycle property to be well defined. So the associativity of the addition, for example, comes from the cocycle property. And then we also go later to a modular space where we take equivalence classes of these surfaces, and then, for example, this diffeomorphism invariance makes it such that we vary in the correct way over the equivalence class of the surface. And what we get is a line bundle when we view this over the moduli space of all of these surfaces, which I will write down next. So this is the moduli space, which is also used in, for example, geometric vertex operator algebras or in Siegel conformal field theory. And it's with connected, compact, genus 0. So this is only the genus 0 part. Riemann surfaces, and then there are n+1 boundaries. Which are enumerated. So they are enumerated like 0 to n. And they have these analytic parametrizations. All the things, and then they are up to isomorphisms. And the isomorphisms are analytical maps which preserve the boundary parameterization. So when you have the two boundaries and the parameterizations, this way, and then some, so these are the boundaries of some surface, and then you have an isomorphism F, then you get this, that this commutes.
Is it important that this is genus 0, or what happens if you had a higher genus surface with some boundaries?
Sure, yeah. I mean, this modular space you can define, but it's not so nice because for genus 0 you can always uniformize to a sphere by putting on caps on all the boundaries, and then you get some complex and analytical description of the boundaries. And so now I can explain to you what is this modular functor. So I will define what this one-dimensional genus 0 modular functor is at the same time as I introduce this real valued one. So there are line bundles, which are these determinant lines here, which are over the modular space. And then we need some analytical structure, and this is by giving a global section. So there are two options for the global section. One is to do this uniformization I just mentioned, which gives you a pullback of the flat metric on the uniformized sphere, which you get by kind of, if you have this surface, then you can put on caps everywhere in a way which is compatible with the boundary, and then you get that this is compatible with isomorphic to a sphere, and then you can pull back the round metric from there. And then you get, or you can actually pull back the flat metric because the 0 will always be here. So this is then, you can take C as a subset and you pull back the flat metric. And what you get is that you can take the pairing between this flat metric and an arbitrary different one, and then just take the equivalence class of that one, and you get a global section. Or you can take the zeta regularized determinant of the Laplacian, which by the Polyakov-Alvarez anomaly formula varies exactly in a way such that if we have these boundary conditions on the metric, then the factor which you get from change in the metric in here is exactly, again, this Liouville action I had at the beginning. And a third thing we need for a modular functor is Sewing isomorphisms. So for modular functor, you see this as some kind of algebraic structure where you can take two surfaces and sew them together in n different ways by taking the zeros boundary of one surface and the i's boundary of another one, and then you sew them together. And we also want to take this sewing operation into the line model. This works as follows. I will just write the map. If we have some, on some surface sigma, we have something in the line bundle, which is always a number and some choice of metric. And then we have a second one, and we sew them together in some way, so we have to choose the boundaries and along which we do this. Then there should be some bilinear map. So it's bilinear in the factors. And because of this restriction on the metric at the boundary you've taken, you can just match the metrics and get a well-defined metric on the product. And this gives you a sewing operation on this line bundle. And all these three properties together with some associativity of the sewing, which again follows from this cocycle property in this case, and some permutation invariance under renumbering of the boundary components, gives you a 1D genus 0 modular functor. Okay, and now this is what I wanted to introduce, but maybe I say now a little bit of what is mathematically also interesting about this modular functor. So maybe I take 1 minute to make it. So, so the question is, among all the one-dimensional genus zero real-valued modular functors, is this somehow a unique one? Because there is this kind of theorem for complex modular functors by Zhu Wang, who called it the Mumford-Segal theorem. And there is a similar thing here. I need to introduce a couple of things. So, for example, there is the diffeomorphism group of the circle, which acts on these moduli spaces by reparametrization. So you take this boundary parametrization and you put some diffeomorphism of the circle along with it, so you get a new surface with a different parametrization. This is an action, and you can define a central extension of this group using the modular functor by saying that the determinate line of such a diffeomorphism is given by the determinate line of some annulus with this action. It's a right action, that's the precomposition. And then you kind of cancel out this annulus again by taking the dual. And on this kind of one-dimensional vector space now associated to phi, you can first of all show that it's independent of the choice of annulus, and then again there is a kind of sewing operation for these two by taking two different diffeomorphisms, and then you somehow sew them together such that this factor cancels with another one. Because it's independent of A, you can do a transformation where A goes to A with the second one, and then you kind of cancel factors. I don't think I have time to write down the computation. And then you get a central extension. And then the central extension of the diffeomorphism group, that's something we know stuff about. So essentially there is two different central extensions. One is the Bott-Thurston cocycle, which gives you the Weyl group. And the other one is something related to the universal cover of this group and to rotation numbers. So if we take F1 and F2 to be lifts of such a diffeomorphism to the universal cover, so they are maps from R to R with some periodicity, then we can take the rotation number of such a thing, I denoted rho, then this particular combination does not depend on the lift anymore, and this is has a cocycle property, so it's a cocycle of the diffeomorphism group, which gives a central extension. And then what you can show is that this one does not appear for one-dimensional genus zero modular functors by some, which I can only say in words. So what you get is that there is not a canonical connection on this central extension, but there are multiple ones, and any of these connections gives you also a connection on the modular functor, which, remember, is a line bundle. And this particular kind of connection is flat on a subspace of surfaces, where we take surfaces whose boundaries are only round circles, so not kind of weirdly deformed ones. And this is a very low-dimensional subspace, and you can the connection is flat there, and you can compute a holonomy in this subspace of the moduli space. And it turns out that this holonomy is trivial, And then you know that because this one, because it's related to the universal cover, is non-trivial, you have you have a contradiction that this one cannot appear for these one-dimensional genus zero modular functors. And then you have and then you know that it must be the Bott-Sersen cocycle, or which I haven't figured out yet, is whether this might actually be trivial. But if it's not, then it should be related to this Bott-Sersen cocycle. Yeah, in this abstract way, it's kind of hard to actually compute this from it. So
in principle, you should be able to calculate the central charge for this.
The central charge is arbitrary. So we started with the central charge here.
So this will be the central. I mean, this is the Virasoro algebra, isn't it?
Yes.
So. So it's basically Virasoro.
Then you have a real valid Lie group, and then if you take the Lie algebra of that and you complexify it, then you get a Virasoro algebra.
Right. So so this cocycle is not the central charge of the Virasoro algebra.
Yes, it is. It is. What I skipped over here is so I put the central charge to 1 over here, but you can see in this definition of the line boundary. And easily put in the central charge again by putting a C here, but the central charge is still arbitrary. But yes, of course, this central charge is then related to the central charge you would get for the algebra. But you don't have a representation, you just have the algebra, so the central charge is just another generator. Yeah, I think that's it then. Thank you.
More questions? So these Laplacian, what boundary conditions do you impose on
Dirichlet boundary conditions.
but is that compatible with gluing, right?
Yeah, it's actually very interesting to look at the gluing for this. There should be some kind of Neumann jump operator if you try to compute this cocycle explicitly. Yeah, then you can. There's two formulas. There's the Fourier-Alvarez anomaly formula, which changes when you change the metric. It gives you a factor. But there's another formula which has to do with the gluing, and there is some jump operator which relates then the determinants.
Okay. More questions? No. Let's thank the speaker again.